Like you, I like to touch computers, and I've concluded that they're pretty cool. But if you look inside a computer, you'll see that it's filled up with ones and zeros. And I think that this is basically just a hack. Why 1? Why 0? It's totally arbitrary. We could have used anything. So I think we can do better. I think we can do best. And consulting all of the ways to do things well, we see mathematics like a candle in the dark calling to us. And the foundation of all of mathematics is the real numbers, which are given to us on computers via IEEE 754 standard, i.e., the floating point numbers. Now, the floating point numbers are just like the real numbers, except that they've been enhanced for computers. So here in green, we see all of the positive numbers. Well, not all of them. You don't get all of the real numbers. In fact, you get almost none of the real numbers are representable, but we have several numbers that are positive, and each of those also has a negative counterpart, including, for example, -0. Now, -0 has some exciting properties, like it's equal to 0, which you might call +0. That's kind of weird. Also, if these other numbers, like infinity, which are not normally found in the real numbers, infinity is what you get if you count really high, or say add up all of the positive numbers, you get it positive infinity, not -1/12 or something really weird like that. There's also a negative infinity, which is what you get if you count really low. Or another way to get infinity would be to divide by 0. And this leads us to another exciting property, which is, we said -0 is equal to +0, but if I say 1 over +0, I get infinity, and if I say 1 over -0, I get negative infinity. So you don't have the normal substitution property. Anyway, suffice to say, floating point numbers are filled with beauty. And, bless our stars, in addition to all these finite and a few infinite numbers, we also have some numbers called not a number, or NaN. And you can get these numbers by, for example, dividing 0 by -0. Now, NaN has the best properties of all. If you take two NaNs and compare them, even if it's the same NaN, then it won't be less than, it won't be greater than, and it won't be equal to itself, which is really, it opens up a world of possibilities, let's just say, in computation. So, okay, so here we have the real numbers. The real numbers are cleaner, more elegant than 1s and 0s, and 1 and 0 right there. We could also have 2 and 3. But we'd like to select some of these numbers to base our new computing on, right? Now, to do this, we're going to need to pick 2 different numbers at least. And sadly, we can't pick NaN and NaN, because although NaN is 2 different numbers, as it is not equal to itself, we also can't tell them apart. So what we're going to do is we're going to pick NaN and another great number with a bunch of excellent properties, which is infinity. And this is a good pair because NaN and inf, or infinity, are sort of maximally far away from one another. They're not even comparable. Whereas, 0 and 1, they're right next to one another, so it's so easy to just confuse them. And as just one more piece of evidence for the beauty of these numbers, let's look at a famous equation known as Euler's identity. And you can see here that e to the I pi it's really close to being something good. Somehow it comes out to -1. But if we're able to involve NaN and infinity in here, then we can find that e to the I pi plus 1 to the NaN times inf equals 0. And this just ties all of the numbers together in a beautiful way. Even if you like 1 and 0, they're in there too. I'll throw a bonus equation up here as well. You can work that one out yourself or see the accompanying paper. And these are actually real, by the way. Now, most programmers are taught or come to believe that NaN is like the GNU public license of numbers, in that if you do anything with a NaN, like 1 plus NaN, you get back NaN. And this is largely true. The same too holds for infinity, actually. If you take infinity and add 1, you get infinity. But at least with infinity, there are some ways out, like 1 over infinity is 0, as we discussed. And actually with NaN, as we saw, there are some formulas that don't produce NaN, like 1 to the NaN is always 1. but 1 to the infinity is always 1. So how are we going to do anything with NaN at infinity? How are we going to compute? Well, if you pore through the IEEE 754 standard, you'll find an interesting function called maxnum. I'm just going to call it max. And this returns the maximum, the larger of its two arguments. But it has a special property, which is if one of the arguments is NaN, then it returns the other argument. And if they're both NaN, then it's going to return NaN. And this is going to provide us with a way out. So let's say we're only ever dealing with NaN and infinity. And so there's 4 different arguments that max can get, 2 times 2. So we can make a table of all of the different outcomes, and we can see that it doesn't always give us the same answer, so that's really good. And just to compare, a function like multiplication gives us a different table of outputs. Now, unfortunately, these two together are incomplete, meaning that there are some tables that I can't create just by combining them. And one way to see that is if we think of NaN as false and infinity as true, although there will be no need for such simplifications, then max function behaves as or, with the multiplication function behaving like and it's a classical result that those are not complete. But not to be deterred, I wrote a computer program to search for functions or expressions that produce the desired tables, and I was able to find, well, all of them. So here's the shortest floating point expression that produces the equivalent of the exclusive OR function. And, well, it's pretty elegant. And then there's this pithy one, which produces the equivalent of the not and function, which I like to call the Nand Gate. And this is a great gate because it's all you need. It's complete on its own without anything else. You can construct all of the other tables with just this function. But before we get into that, let's take a look at why it works. So looking at the top right case there, we have x is NaN and y is infinity. And so if we substitute those in for x and y, we find that, well, x plus y is going to be NaN because NaN plus infinity is NaN. And then we have max of NaN and something, so that's always the other thing. And then we have infinity minus negative infinity, which is infinity plus infinity, which is infinity, as desired. And over here, where both arguments are infinity, we're going to add them together and get infinity. And then we'll have max of positive infinity and negative infinity, which is, of course, positive infinity, much larger. But then we have infinity minus infinity. And because we don't know which of the two infinities is bigger, the result in floating point is NaN, and so that's what we get as desired. So we're pretty much done. You can use the NaN gate to create all the other gates, and you can learn how to do that on Wikipedia. I'm not going to go through it here. The rest is really just a matter of engineering. But in order to do some engineering, we need to think about how we're going to represent floating point numbers and do so efficiently. A floating point number is usually represented in a kind of scientific notation, but using base 2 instead of base 10. And typically you'd use 32 bits or 64 bits for this. In the 32-bit case, we have 1 sign bit and 8 bits to describe the exponent, with the remainder used to describe the mantissa, which is that sort of decimal part. But this is way too many bits for our purposes. We only need to represent NaN at infinity, so 32 is way too many. And some people will use 16-bit floats or 8-bit floats even for machine learning applications. But consulting the specification again, I found that, in fact, it's legal, it's seemingly legal, to have a 3-bit floating point representation where you have just 1 bit for the sign and for the exponent and for the mantissa. Now, as far as I know, no one has ever actually used binary 3 format, probably because there's only 8 values. Here they all are. And most of them are kind of nuts, like infinity and negative 0 and so on. So the only like regular numbers in there are 0, 1, and negative 1. But, you know, if you like 0 and 1, there they are again. So we're nearly done. But if we want to not just think about this computer, but touch it, and I do, then software is not really going to suffice. Plus, software is so slow, and it's not, you know, hardcore like hardware is. So let's fire up that Schematic Editor. So here we have the STM32F303RDT6, which is a little microprocessor that has hardware floating point. And it has 64 pins on it. And so that's actually a lot. And I was able to pack in 5 NaN gates, there's all 5, onto this package, each of which takes in a floating point number encoded as a binary 3, and another one of those, and then runs that function we've been describing, the NaN gate, and outputs another binary 3 floating point number. So I got 5 of those. And this chip will be running actual floating point instructions
via a program that I wrote that I load onto it, of course, that takes those 3-bit floating point numbers, expands them into 32-bit floating point numbers, runs the function, packs them back into 3-bit, and so on. But there's a problem with that, which is that each of those pins will be receiving or sending a bit as a 1 or a 0 logic level. And that means we've got 1s and 0s still all over the place. So of course what we really want to do is use these NaN gates together in order to construct a meta NaN gate so that each of the pins is actually represented by a floating point number represented in binary 3. So here's what the full schematic looks like. In order to implement that function on all combinations of binary 3 floating point numbers, I need 14 gates, so that uses up 3 of these microprocessors all wired together. And each of the microprocessors needs some support components for it, like power supply filtration and a crystal oscillator and an interface for programming it and so on. And all of that together totals 18 inputs and 9 outputs, so there are 27 pins that connect up to a Raspberry Pi, which can be used to drive this thing, or rather the Raspberry Pi can use it as an accelerator for mathematics. Of course, that's just the schematic. You also need to decide where the parts go and how they all connect up together physically. And so here is the printed circuit board layout. It actually got pretty involved, and this was only my second circuit board ever, so that's like a good puzzle. And the minimum order size is 10, so you want to get it right, so at least you have 9 extra boards that are correct. Then just get set up to solder. The chips are pretty small. Here they are shown next to a Bermuda quarter for scale. Touching these is forbidden due to oils and electrostatic discharge, so we use the forceps. It's certainly not because I have steady surgeon hands. The shmoo here is acid flux paste, which helps it stick in place while I'm doing that, but it's mostly for the next part, which is soldering. Now, I've done a lot of soldering in my life, but these were pretty tricky. If you're going to do it by hand, pretty much the only thing you can do is put a big blob across all of the pins, which is of course no good because then they're all connected electrically. And then you can desolder using one of these wicking braids, and somehow it leaves the solder connecting to the pads but not the bridging between the pins, which is like magic to me. On the other hand, these through-hole parts making this little miniature city are just a joy to do. They're so easy in comparison. Then it's ready to attach to this Raspberry Pi, which I can use to program the chip and to test it. Later on, I'll be soldering a smaller Raspberry Pi directly to this board. This part of the process is terrifying, by the way, because there's so many ways to screw it up. I could have routed the board wrong, I could have misunderstood the data sheet, I could have got defective parts or fried them myself or soldered it wrong, and most of these issues just cause like an undebuggable, empty, non-working dead board. So it was very exciting when I actually got it to successfully program the ROM, even to recognize that it was there. Here's what that exciting message looks like. Then just do that same thing 2 more times. Here the board fully assembled on a Belizean $2 note for scale. So now we're almost done. We just need to figure out what to do with what we've built. And again, what we've built here is a board that implements a single NaN gate using floating point instructions, except that each of the bits of the floating point numbers are themselves represented by floating point numbers. Does it make sense? Anyway, don't worry about too much that part. We have this Raspberry Pi attached to it, and what we want to do is then use that to build a computer. And I'm going to call this the Nandy 1000. It will not include a monitor. It will not include any software or OS. It doesn't have any blinking lights. So we're going to want to be satisfied with the computation itself, just the beauty of this thing humming along, doing what it does. Now, I'm not going to be able to describe the architecture in detail, but I can at least throw it up on a slide. Basically, the memory of the computer will consist of a d-dimensional cube indexed by floating point numbers. So there's 8 positions for each one, because these are binary 3 floats. And then an instruction consists of 3 floating point numbers, which always breaks down into an opcode, a register, and a literal. And you can see what these operations do. You'll see that we have the plus, minus, and max functions on floating point numbers, which is nice because we know that we can use those to code up any function that we like. And there's some complexity here to deal with the fact that opcodes are so short, but you have a lot of addressable memory.
And speaking of complexity, I can implement this architecture completely with NAND gates, as alluded to. And, well, it turns out to be millions of NAND gates, at least if you use a dimension of 4. If I just use a one-dimensional NAND 1000, which is just 8 memory cells, then I can at least fit the network on this screen. This is what it looks like. Good luck with this, MPEG. As usual, I tried some off-the-shelf software and it crapped out, so I had to write my own visualization, which is mediocre. There we can see an important node with lots of outputs. And the full network, this is just a one-dimensional one. The four-dimensional one would be about 36 times bigger than this, which is big, but not too big to fit on the Raspberry Pi, so that's what we do. The whole state of the NAND 1000 is stored inside the Raspberry Pi's memory. That's the top row there. Each one of those is a NaN or an infinity. And then repeatedly what we're going to do is find a gate that has its inputs with some values that are known, but we don't know what the output is yet. And we're going to pass those values to the board to run this in hardware, because that's more elegant. So if this gate's input is NaN and infinity, then I encode each of those as binary 3 numbers whose bits are, of course, represented with NaN and infinity, pass those to the board, and then it does the floating point math and computes the result. I get that back on the Raspberry Pi, and I use that to fill in that one gate's value. And I can just keep doing that until I get to the bottom and the entire new machine state is set. Now, to do just one of those NAND gates on the board takes a few milliseconds. And so for this whole network, it's actually rather a lot of time. Even after I optimized the network down to about half the size, well, you can see here, I'll run the command, and just to run one instruction on the processor, it has to do those 920,000 gates. And this is about as fast as it can get through them. So while we wait for that, let's put the finishing touches on the NAND 1000 with a beautiful custom enclosure. The keyboard, of course, is purely decorative, as is the power switch and floppy drive. This computer will do nothing visible. We're going to be content just knowing that it's doing beautiful computation on the inside. All I ever do with computers anyway is do other computer stuff, so I figure I can save the trouble. Now, 3D printing is the perfect match for the NAND 1000 because it's super slow and it just barely works. Like so here, I printed for a few hours and now it's just printing air. And now a new one, a few hours later, it got detached and it's just moving it around, pooping its plastic noodle all over it. So use a raft, which is a way to get it to stick to the platter better. Well, that didn't work either. But if you just keep trying, eventually you can get something that's pretty nice. Of course, you measured it wrong, and the board doesn't quite fit in there, but close enough. Okay, so the NAND 1000 has finally finished executing one instruction, and that took about 24 minutes. So in a computer simulation, I was able to run, 458,000 instructions per second. So if on the hardware I can get one instruction for 24 minutes, that's about a 150 billion% speed down, which is it's pretty good. But of course, speed is not what we're after here. We're after just beautiful computation going on inside the heart of this machine. And here it is doing that. Every time it boots, it just fills itself up with a random scrambled program and executes those beautiful mathematical operations. Gosh, I just want to touch it. I'm going to touch it.